First of all, welcome back to today's class, day number 17 of MATH113, section 7, applications of mathematics in today's world. So if you look at the Y screen here, I have a very brief summary of what we have gone through so far in calculus. Okay, a little bit of the small character, but still you can see it, so let me enlarge the character a little bit. We have gone through the study of calculus by going through part A, some definitions and some basic rules, including the introductions to derivatives, examples of derivatives, derivative at rate of change, limits and continuity, discontinuity, calculating the derivatives, derivative of sine and cosine, limits of sine and cosine, product rule, cosine rule, chain rule, and a little bit on higher derivatives. So this is what we call part A, and all of these include lectures number 1, number 2, number 3, and number 4. And the sources of those information comes from MIT OpenCourseWare, number 1801, single variable calculus. Okay? So the second part that we have gone through after the first part is called implicit differentiations and inverse function. I just want you to know that where we are, so we have to make sure you understand where we are. We've gone through part B of differentiations on implicit differentiations and inverse functions, including section 13, implicit differentiations, 14 examples of implicit differentiations, and implicit differentiations and inverse functions, as well as the very important derivative of a to the power x. The exponential functions is derivative and its inverse, which is the natural logarithm. The derivatives of other exponential functions, an interesting limit involving e, the magic number that is created for calculus. We did not cover hyperbolic trigonometry functions. Okay, this part we did not cover, but you can read and study them. And so today we come to the applications of differentiations. We officially start to help you learn this, although we've covered something in this area. And when we start today, we're going to learn the approximations and the curve sketching technique using the calculus, the foundations of all of these. And what we're going to do this week, we hope that we can finish them all, is including sections 23, linear approximations, examples of linear approximations, and then we move to introductions to quadratic approximations, using quadratic approximations when and why, and then sketch the graph using polynomials and rational functions, and then sketch the graph again in terms of the general strategies. Okay? So these are very exciting topics. Now, before we officially begin this, allow me to bring you back to where we are last time. Last time, we were at visiting back to day number 11, and we would like to invite you to use the very useful video from Khan's Academy to help yourself to understand the meaning of critical point. You should have a good understanding of this now, and some basic graphing of functions. We involved minima, maxima, both local and global, and those critical points. We know how to find the critical numbers. You need to understand how to test critical point for the local extrema, whether or not it's a maximum point or a minimum point. And you should know how to find a minimum and a maximum for typical polynomial functions like this. And indeed, we're going to revisit them this week. And you also have learned the derivatives of some inverse functions from Khan's Academy, the derivative inverse sine, derivative inverse cosine, derivative inverse tangent, the derivative natural logarithm, derivative x to the power x, derivative using dot properties. All of these we have discussed about it. And then Professor Gilbert Strand, from his high-minded calculus using minima and maximums, the introductions, he introduced to us the meaning of concavities, bending downward, inflection form, all right? And also convexity, convex, bending upwards. So you will come back to this, to revisit this after you've learned the official lessons today. So let's save some time now. Let's go directly to Professor David Jerrison's lecture, that is lecture number 9. Please get ready and learn.
Educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
We're starting a new unit today, and so this is Unit 2, and it's called Applications. Of differentiation. Okay? So the first application, and we're going to do 2 today, is what are known as linear approximations. Whoops, that should have 2 P's in it. Approximations. So that can be summarized with one formula, but it's going to take us at least half an hour to explain how this formula is used. So here's the formula. It's f of x is approximately equal to its value at a base point plus the derivative times x minus x0. All right, so this is the main formula for right now. Put it in a box. And let me just describe what it means first, and then I'll describe what it means again and several other times. So first of all, what it means is that if you have a curve, which is y equals f of x, it's approximately the same as its tangent line. So this other side is the equation of the tangent line. So let's give an example. I'm going to take the function f of x, which is log x, and then its derivative is 1 over x. And so let's take the base point x0 is equal to 1. That's pretty much the only place where we know the logarithm for sure. And so what we plug in here now are the values. So f of 1 is the log of 0, or sorry, the log of 1, which is 0. And f prime of 1, well, that's 1 over 1, which is 1. All right? So now we have an approximation formula, which if I copy down what's right up here, it's going to be log x is approximately, so f of 0 is 0, right? Plus 1 times x minus 1. All right? So I plugged in here for x0 3 places. I evaluated the coefficients, and this is the dependent variable. So all told, if you like, what I have here is that the logarithm of x is approximately x minus 1. And let me draw a picture of this. So here's the graph of log x. And then I'll draw in the tangent line at the place that we're considering, which is x equals 1. So here's the tangent line. All right, it's separated a little bit, but really I probably should have drawn it a little closer there to show you. The whole point is that these two are nearby. But they're not nearby everywhere. So this is the line y equals x minus 1. That's the tangent line. They're nearby only when x is near 1. So say in this little realm here. So when x is approximately 1, this is true. Once you get a little farther away, this straight line, the straight green line, will separate from the graph. But near this place, they're close together. All right, so the idea, again, is that the curved line is approximately the tangent line. And this is one example of it. All right, so I want to explain this in one more way, and then we want to discuss it systematically. So the second way that I want to describe this requires me to remind you what the definition of the derivative is. So the definition of a derivative is that it's the limit as delta x goes to 0 of delta f over delta x. That's one way of writing it. All right? And this is the way we defined it. And one of the things that we did in the first unit was we looked at this backwards. We used the derivative, knowing the derivatives of functions, to evaluate some limits. So you were supposed to do that on your hour test. There were some examples there, at least one example, where that was the easiest way to do the problem. So in other words, you can read this equation both ways. This is really, of course, the same equation written twice. Now, what's new about what we're going to do now is that we're going to take this expression here, delta f over delta x, and we're going to say, well, when delta x is fairly near 0, this expression is going to be fairly close to the limiting value. So this is approximately f prime of x, 0. All right, so that, I claim, is the same as what's in the box in pink that I have over here. All right, so this approximation formula here is the same as this one. This is an average rate of change, and this is an infinitesimal rate of change, and they're nearly the same. That's the claim. So you'll have various exercises in which this approximation is the useful one to use, and I will, as I said, I'll be illustrating this a little bit today. Now, let me just explain why those two formulas in the boxes are the same, all right? So let's just start over here and explain that. So the smaller box is the same thing if I multiply through by delta x, as delta f is approximately f prime of x 0 delta x. All right? And now if I just write out what this is, it's f of x, minus f of x 0. I'm going to write it this way, which is approximately f prime of x 0, and this is x minus x 0. So here I'm using the notations delta x as x minus x 0. And so this is the change in f. This is just rewriting what delta x is. And now, the last step is just to put the constant on the other side. So f of x is approximately f of x 0 plus f prime of x minus x 0. So this is exactly what I had just to begin with. All right? So these two are just algebraically the same statement. There's one other way of looking at it. All right, so now I want to go through some systematic discussion here of several linear approximations, which you're going to be wanting to memorize. And rather than it's being hard to memorize these, it's supposed to remind you, so you'll have a lot of extra reinforcement in remembering derivatives of all kinds. So when we carry out these systematic discussions, we want to make things absolutely as simple as possible. And so one of the things that we do is we always use the base point to be x0. So I'm always going to have x0 is equal to 0 in these standard list of formulas that I'm going to use. And if I put x0 equals 0, then this formula becomes f of x a little bit simpler to read. It becomes f of x is f of 0 plus f prime of 0 times x. All right? So this is probably the form that you'll want to remember most. That's, again, just a linear approximation. But one always has to remember, and this is a very important thing, this one only works near x is 1. This approximation here really only works when x is near x0. All right, so that's a little addition that you need to throw in. So this one works when x is near 0. Right? You can't expect it to be true far away. The curve can go anywhere it wants when it's far away from the point of tangency. So, okay, so let's work this out. Let's do it for the sine function, for the cosine function, and for e to the x to begin with. Yeah, question? Yeah, when does this one work? Well, so the question was, when does this one work? Again, this is when x is approximately x0, because it's actually the same as this one over here. Okay? And indeed, that's what's going on when we take this limiting value. Delta x going to 0 is the same. Delta x is small. So another way of saying it is that delta x is small. Now, exactly what we mean by small will also be explained. But it is a matter of, to some extent, of intuition as to how good it is. In practical cases, people will really care about how small it is before the approximation is useful. And that's a serious issue. All right, so let me carry out these approximations for x. Again, this is always for x near 0. All right? So all of these are going to be for x near 0. So in order to make this computation, I have to evaluate the function. I need to plug in two numbers here in order to get this expression. I need to know what f of 0 is, and I need to know what f prime of 0 is. If this is the function f of x, then I'm going to make a little table over to the right here with f prime, and then I'm going to evaluate f of 0, and then I'm going to evaluate f prime of 0, and then read off what the answers are. Right? So first of all, if the function is sine x, the derivative is cosine x. The value of f at 0, that's sine of 0, is 0. The derivative is cosine. Cosine of 0 is 1. So there we go. So now we have the coefficients 0 and 1. So this number is 0, and this number is 1. So what we get here is 0 plus 1 times x. So this is approximately x. All right, there's the linear approximation to sine x. Similarly, so now this is a routine matter to just read this off for this table. We'll do it for the cosine function. If you differentiate the cosine, what you get is negative sine x. All right? The value at 0 is 1. So that's cosine of 0 at 1. The value of this minus sine at 0 is 0. So this is, going back over here, 1 plus 0 times x. So this is approximately 1. This linear function happens to be constant. And finally, if I do e to the x, its derivative is again e to the x. And its value at 0 is 1. The value of the derivative at 0 is also 1. So both of the terms here, f of 0 and f prime of 0, they're both 1, and we get 1 plus x. All right, so these are the linear approximations. You can memorize these. You'll probably remember them either this way or that way. This collection of information here encodes the same collection of information as we have over here for the values of the function and the values of their derivatives at 0. So let me just emphasize again the geometric point of view by drawing pictures of these results. So first of all, for the sine function, here's the sine, well, close enough, okay? So that's, boy, now that is quite some sine. Let's try to make the two bumps be the same height, roughly speaking, all right? Anyway, the tangent line we're talking about is here, and this is y equals x, and this is the function sine x. And near 0, those things coincide pretty closely. The cosine function, I'll put that underneath, I guess. I think I can fit it. Make it a little smaller here. All right. So for the cosine function, we're up here. It's y equals 1. Well, no wonder the tangent line is constant. It's horizontal. All right. The tangent line is horizontal, so the function corresponding is constant. So this is y equals cosine x. All right. And finally, if I draw y equals e to the x, that's coming down like this, and the tangent line is here, and it's y equals 1 plus x. The value is 1, and the slope is 1. All right, so this is how to remember it graphically, if you like. This analytic picture is extremely important and will help you to deal with sines, cosines, and exponentials. Yeah, question? The question is, what do you normally use linear approximations for? Good question. We're getting there. First, we're getting a little library of them, and I'll give you a few examples. Okay, so now, I need to finish the catalog with 2 more examples, which are just a little bit, slightly more challenging, and a little bit less obvious. So, the next couple that we're going to do are log of 1 plus x and 1 plus x to the power r. Okay, these are the last 2 that we're going to write down and that you need to think about. Now, the procedure is the same as over here. Namely, I have to write down f prime, and I have to write down f of 0, and I have to write down f prime of 0, and then I'll have the coefficients to be able to fill in what the approximation is. So f prime is 1 over 1 plus x in the case of the logarithm, and f of 0, if I plug in, that's log of 1, which is 0. And f prime, if I plug in 0 here, I get 1. And similarly, if I do it for this one, I get r, 1 plus x to the r minus 1. And when I plug in f of 0, I get 1 to the r, which is 1. And here I get r times 1 to the r minus 1, which is r. All right? So the corresponding statement here is that log 1 plus x is approximately x, and 1 plus x to the r is approximately 1 plus rx. All right? That's 0 plus 1 times x, and here we have 1 plus r times x. And now, I do want to make a connection, explain to you what's going on here in the connection with the first example. We already did the logarithm once. Let's just point out that these 2 computations are the same, or practically the same. Here I use the base point 1, but because of my sort of convenient form, which will end up, I claim, being much more convenient for pretty much every purpose, we want to do these things near x is approximately 0. All right? You cannot expand a logarithm and understand the tangent line for it at x equals 0, because it goes down to minus infinity. Similarly, if you try to graph 1 plus x to the r, or x to the r, without the 1 here, you'll discover that sometimes the slope is infinite, and so forth. So this is a bad choice of point. 1 is a much better choice of a place to expand around. And then we shift things so that it looks like it's x equals 0 by shifting by the 1. So the connection with the previous example is that what we wrote before I could write as the logarithm of u is u minus 1. Right? That's just recopying what I have over here, except with the letter u rather than the letter x. And then I plug in u is equal to 1 plus x. And then that, if I copy it down, you see that I have a u in place of 1 plus x, that's the same as this. And if I write out u minus 1, if I subtract 1 from u, that means that it's x. So that's what's on the right-hand side. So these are the same computation. I've just changed the variable. All right. So now I want to try to address the question that was asked about how this is used and what the importance is. And what I'm going to do is just give you one example here and then try to emphasize the first way in which this is a useful idea. Or maybe this is the second example, if you like. So we'll call this example 2 maybe, since we already know. So let's just take the logarithm of 1.1. Just a second. Let's take the logarithm of 1.1. So I claim that according to our rules, I can glance at this and I can immediately see that it's approximately a tenth. So what did I use here? I used that the log of 1 plus x is approximately x, and the value of x that I used was a tenth. All right, so that is the formula. So maybe I should put a box around these two formulas too. That's this formula here applied with x equals a tenth. I'm claiming that a tenth is a sufficiently small number, sufficiently close to 0. This is an okay statement. All right? Now, so the first question I want to ask you is, which do you think is a more complicated thing? The left-hand side or the right-hand side? I claim that this is a more complicated thing. You'd have to go to a calculator to punch out and figure out what this thing is. This is easy. You know what a tenth is. All right? So the distinction that I want to make is that this is hard, and this is easy. All right? Now, that may look contradictory, but I want to just do it right above as well. This is hard, and this is easy. Okay? This looks uglier, but actually this is the hard one. And this is giving us information about it. Now, let me show you why that's true. Look down this column here. These are the hard ones, hard functions. These are the easy functions. What's easier than this? Nothing. Okay? Well, yeah, 0, that's easy. But, okay, over here it gets even worse. These are the hard functions, and these are the easy ones. All right? So that's the main advantage of linear approximation, is you get something much simpler to deal with. And if you've made a valid approximation, you can make much progress on problems. Okay, we'll be doing some more examples, but I saw some more questions before I made that point. Yeah? Is this ln of 1.1 or what? This is a parens there. It's ln of 1.1. It's the digital number, right? I guess I've never used that before, a decimal point, have I? I don't know. Okay, other questions? Okay, so let's continue here. Let me give you some more examples where it becomes even more vivid, if you like, that this approximation is giving us something a little simpler to deal with. So here's example 3. I want to find the linear approximation near x equals 0. I also, when I write this expression near x equals 0, that's the same thing as this. That's the same thing as saying x is approximately 0, all right? Of the function e to the minus 3x divided by square root 1 plus x. All right? So here's a function. Okay, now, what I claim I want to use for the purposes of this approximation are just the sum of the approximation formulas that we've already derived. All right? And just to combine them algebraically. So I'm not going to do any calculus. I'm just going to remember. So with e to the minus 3x, it's pretty clear that I should be using this formula for e to the x. For the other one, it may be slightly less obvious, but we have powers of 1 plus x over here. All right? So let's plug those in. I'll put this up so that you can remember it. And we're going to carry out this approximation. So first of all, I'm going to write this so that it's slightly more suggestive. Namely, I'm going to write it as a product. And there you can now see the exponent. In this case, r equals minus a half that we're going to use. Okay? So now I have e to the minus 3x, 1 plus x to the minus a half, and that's going to be approximately, well, I'm going to use this formula. I have to use it correctly. X is replaced by minus 3x, so this is 1 minus 3x. And then over here, I can just copy verbatim the other approximation formula with r equals minus a half. So this is times 1 minus a half x. All right? And now, I'm going to carry out the multiplication. So this is 1 minus 3x minus a half x plus 3 halves x squared. Okay, so now, here's our formula. So now this isn't where things stop. And indeed, in this kind of arithmetic that I'm describing now, things are actually easier than they are in ordinary algebra and arithmetic. The reason is that there's another step which I'm now going to perform, which is that I'm going to throw away this term here. All right? I'm going to ignore it. In fact, I didn't even have to work it out because I'm going to throw it away. So the reason is that already when I passed from this expression to this one, that is from this type of thing to this thing, I was already throwing away quadratic and higher order terms. So this isn't the only quadratic term. There are tons of them. I have to ignore all of them if I'm going to ignore some of them. And in fact, I only want to be left with the linear stuff, because that's all I'm really getting a valid computation for. So this is approximately 1 minus, so let's see, it's a total of 7 halves x. All right? And this is the answer. This is the linear part. So the x squared term is negligible. So we drop x squared terms and higher. All right, all those terms should be lower order. If you imagine x is a 10th or maybe a 100th, then these terms will end up being much smaller. All right, so we have a rather crude approach, and that's really the simplicity, and that's the savings. Okay, So now, since this unit is called applications, and these are indeed applications to math, I also wanted to give you a real-life application, or a place where linear approximations come up in real life. So maybe we'll call this example 4. This is supposedly a real-life example. I'll try to persuade you that it is. So I like this example because it's got a lot of math as well as physics in it. So here I am on the surface of the Earth, and here is a satellite going this way at some velocity v, okay? And this satellite has a clock on it because this is a GPS satellite, and it has a time t, okay? But I have a watch, in fact it's right here, and I have a time which I keep, which is t prime. And there's an interesting relationship between t and t prime, which is called time dilation. And this is from special relativity. And it's the following formula. T prime is equal to t divided by the square root of 1 minus v squared over c squared, where v is the velocity of the satellite and c is the speed of light. Okay, so now I'd like to get a rough idea of how different my watch is from the clock on the satellite. All right, so I'm going to use this same approximation. We've already used it once. I'm going to write t, but now let me just remind you, the situation here is we have something of the form 1 minus u to the minus 1/2. All right, that's what's happening when I multiply through here. So with u equal to v squared over c squared. All right, so in real life, of course, the expression that you're going to use the linear approximation on isn't necessarily itself linear. It can be any physical quantity. So in this case, it's v squared over c squared. And now the approximation formula says that this is approximately equal to, well, again, it's the same rule. There's an r, and then x is minus u. So this is minus minus a half, so it's 1 plus a half u. All right? So this is approximately, by the same rule, this is t prime is approximately t times 1 plus a half v squared over c squared. Now, I promised you that this would be a real-life problem, so the question is, when people were designing these GPS systems, they run clocks in the satellites. You're down there, you're making your measurements, you're talking to the satellite or you're receiving its signals from its radio. The question is this going to cause problems in the transmission? And there are dozens of such problems that you have to check for. So in this case, what actually happens is that v is about 4 kilometers per second. That's how fast the GPS satellites actually go. In fact, they had to decide to put them at a certain altitude, and they could have tweaked this if they had put them at different places. Anyway, the speed of light is 3 times 10 to the 5th kilometers per second. All right? So this number, v squared over c squared, is approximately 10 to the minus 10th. All right? Now, if you actually keep track of how much of an error that would make in a GPS location, what you would find is maybe it's a millimeter or something like that. So in fact, it doesn't matter. So that's nice. But in fact, the engineers who were designing these systems actually did use this very computation, exactly this. And the way that they used it was they decided that because the clocks were different, when the satellite broadcasts its radio frequency, that frequency would be shifted, would be offset. And they decided that the fidelity was so important that they would send the satellites off with this kind of, exactly this offset to compensate for the way the signal is. So from the point of view of good reception on your little GPS device, they changed the frequency at which the transmitter in the satellites, according to exactly this rule. And incidentally, the reason why they ignored higher order terms, the sort of quadratic terms, is that if you take u squared, that's a size 10 to the minus 20th. And that really is totally negligible. That doesn't matter to any measurement at all. That's on the order of nanometers, and it's not important for any of the uses to which GPS is put. Okay, so that's a real example of a use of linear approximations. All right, so let's take a little pause here. I'm going to now switch gears and talk about quadratic approximations. But before I do that, let's have some more questions. Yeah? Okay, so the question was asked, suppose I did this by a different method, all right? Suppose I applied the original formula here. Namely, I defined the function f of x, which was this function here, all right? And then I plugged in its value at x equals 0 and the value of its derivative at x equals 0. So the answer is yes. It's also true that if I call this function f of x, then it must be true that the linear approximation is f of x 0 plus f prime of, I'm sorry, it's at 0, so it's f of x 0, f prime of x 0 times x, right? So that should be true. That's the formula that we're using. It's up there in pink also, all right? So this is the formula. So now what about f of 0? Well, if I plug in 0 here, I get 1 times 1, so this thing is 1. So that's no surprise, and that's what I got. All right? If I computed f prime by the product rule, it would be an annoying, somewhat long computation. And because of what we've just done, we know what it has to be. It has to be -7/2. Because this is a shortcut for doing it. This is faster than doing it. But of course, that's a legal way of doing it. When you get to second derivatives, you'll quickly discover that this method that I just described is complicated, but far superior to differentiating this expression twice. Would you have to throw away an x squared term if you differentiated? No. And in fact, we didn't really have to do that here. If you differentiate and then plug in x equals 0, so if you differentiate this and you plug in x equals 0, you get -7/2. If you differentiate this and you plug in x equals 0, this term still drops out because it's just a 3x when you differentiate. And then when you plug in x equals 0, it's gone too. And similarly, if you're up here, it goes away, and similarly over here, it goes away. So the higher order terms never influence this computation. This just captures the linear features of the function. All right, so now I want to go on to quadratic approximation, and now we're going to elaborate on this formula.
It's a lot of simplifications.
So,
not very accurate, but very useful.
Linear approximation, huh? Well, that should have been linear approximation. Linear. Okay, so that was wrong. But now we're going to change it to quadratic. So suppose we talk about a quadratic approximation. Now, the quadratic approximation is going to be just an elaboration, one more step of detail from the linear. In other words, it's an extension of the linear approximation. And so we're adding one more term here. And the extra term turns out to be related to the second derivative, but there's a factor of 2. All right? So this is the formula for the quadratic approximation. And this chunk of it, of course, is the linear part. This time I'll spell linear correctly. So the linear part is the first piece, and the quadratic part is the second piece. Now, I want to develop the same catalog of functions as I had before. In other words, I want to extend our formulas to the higher order terms. And if you do that for this example here, maybe I'll even illustrate with this example before I go on. If you do it with this example here, just to give you a flavor for what goes on, what turns out to be the case, so this is the linear version, and now I'm going to compare it to the quadratic version. So the quadratic version turns out to be this. That's what turns out to be the quadratic approximation. And when I use this example here, so this is 1.1, which is the same as log of 1 plus a tenth, right? So that's approximately a tenth minus a half 1/10 squared, right? So 1/200th. So that turns out, instead of being a tenth, that's what is it, 0.95 or something like that. It's a little bit less, all right? It's not 0.1, but it's pretty close. Okay, so if you like, the correction is lower in the decimal expansion. All right, so now let me actually check a few of these. I'll carry them out, and what I'm going to probably save for next time is explaining to you. So this is y is factor of a half, and we're going to do this later. Do this next time. You can certainly do well to stick with this presentation for one more lecture so we can see this reinforced. All right? So now I'm going to work out these derivatives. Of the higher order terms. And let me do it for the x approximately 0 case. So first of all, I want to add in the extra term here. All right, here's the extra term for the quadratic part. And now, in order to figure out what's going on, I'm going to need to compute also second derivatives. So here I need a second derivative, and I need to throw in the value of that second derivative at 0. All right, so this is what I'm going to need to compute. So if I do it, for example, for the sine function, I already have the linear part. I need this last bit. So I differentiate the sine function twice, and I claim minus the sine function. The first derivative is the cosine, and the cosine derivative is minus the sine. And when I evaluate it at 0, I get, lo and behold, 0. Sine of 0 is 0. So actually, the quadratic approximation is the same. It's 0 times x squared. There's no x squared term. So that's why this is such a terrific approximation. It's also the quadratic approximation. For the cosine function, if you differentiate twice, you get the derivative is this minus the sine, and the derivative of that is minus the cosine. All right, so that's f double prime. And now, if I evaluate that at 0, I get -1. And so the term that I have to plug in here, this -1, is the coefficient that appears right here. So I need a minus a half x squared. Right? And if you do it for the e to the x, you get an e to the x, and you get a 1, and so you get a plus a half x squared. All right? Now, I'm going to finish these two in just a second, but I first want to tell you about the geometric significance of this quadratic term. So here we go, geometric significance of the quadratic term. So the geometric significance is best to describe just by drawing a picture here. And I'm going to draw the picture of the cosine function. And remember, we already had the tangent line. So the tangent line was this horizontal here. All right? And that was y equals 1. But you can see intuitively, that doesn't even tell you whether this function is above or below 1 there. It doesn't tell you much. It's sort of begging for there to be a little more information to tell us what the function is doing nearby. And indeed, that's what this second expression does for us. It's some kind of parabola underneath here. So this is y equals 1 minus a half x squared, which is a much better fit to the curve than the horizontal line. All right? And this is, if you like, this is the best fit parabola. So it's going to be the closest parabola to the curve, and that's more or less the significance. It's much, much closer. All right, I want to give you, well, so I think we'll save these other derivations for next time because I think we're out of time now. So we'll do these next time.
Well, so today you have actually learned the idea of the linear approximations, which is making things simple. And you can see the applications already. We can actually use the linear approximation to express sine in terms of a series, cosine in terms of a series, and the magic number exponential in terms of another series. And also today you've got a little bit of the quadratic exponentials. So why not try some of the problems now? Let me give you typical problems so that you can use. Now let's try the first one, okay? Let's try the first one, the practice in class. Let's do this. Not this box. That's right here. Okay, this is the important formula. Let me just make sure that you can use it. Okay, get familiar with this formula first. This is for linear approximations on the particular notes, and then I get to the very important parts, I think. Yeah. Let's try to see if we could. This time is a little bit different because we do not have the video for this, but let's show you the problem and let's see if you can apply what you've learned there. Not exactly, but take a look at the values. Can you use linear approximations with the sine functions and upon x and use your answer upon x to approximate the values of sine dot 0, 1, dot 1, and 1. You can check your answer with your calculator if you have one, but I can show you the answer in a minute. You know the answer to sine equal to 0, right? You know that. Which is what? 0. All right? But what if it is not 0? It is a number which is very close to 0 but it's not 0, can you just learn how to use what you've learned here to calculate this? All right? A very simple formula. Will you try? We have about 15 minutes time to get this done. All right? And of course, discussions among the table members are highly encouraged. In the meantime, please help, if you could, by giving me your team number and compositions. I got the first team, I got the second team, I got the third team, all right? I got the fourth team, now it's broken up into 2 smaller teams, and then no more. So, if you have not given me the team compositions, please help by copying this table and by clicking on reply so that I know what your team composition is. All right? Allow me to take attendance for the day through. Wicky, thank you. Johnson, thank you. Alex, not here. Stella, thank you. Viviana, thank you. Jordan, thank you. Star, thank you. Chaos, thank you. Novia, thank you. Luis, thank you. David is not here today. Shenzhen, thank you. Viola, thank you. Candy, thank you. Mailing, thank you. Iris, thank you. Bella, thank you. All right. Cindy, thank you. Vivian, thank you. Patrick, yes, thank you. Jeanette, thank you. Ivy, thank you. Cynthia, thank you. Michelle, thank you. Lizzie, thank you. Second page. Doris, thank you. Kelvin, thank you. Jeremy, thank you. Andy is not here today. So spend a little bit more time with this particular equation to solve this particular question. Okay? Okay, 5 minutes. You have 3 more minutes. It's simple, but it's easy to get into mistakes. Remember, x near to 0. Okay, the particular values calculated must be very much near to the point where x is equal to x0. And this point in 0 is equal to 0, all right? Wow! Are you sure? Look at that. When when we calculate the specific values of f of 0, f pi of 0, it involves the sine and cosine. And so we write this down for a particular sine value here. We got this values. Okay? And when we got this into the approximation, this is the decimal number we got. Well, you can put your fears at rest. If we need to use calculator to do this during the midterm exam, you will be allowed to use your calculator. Okay? Normally, we do not do a lot of things like this in the exam. Take a look at this. So the idea behind the linear approximation is what? Why do we need to learn this? Because the applications of derivative helps to calculate something complicated in a very simple way. Yeah, because simple answer will be good enough. Okay, let's try a typical examples using 10 minutes time this time.
Hi, welcome back to recitation. In lecture, you've been talking about implicitly defined functions and implicit differentiation. So one of the reasons that these are important is, or that implicit differentiation is important, is that sometimes you have a function defined implicitly and you can't solve for it. You don't have any algebraic method for computing the function values as a formula set. So, for example, this function that I've written on the board that I've called w of x is defined implicitly by the equation that w of x plus 1 quantity times e to the w of x is equal to x for all x. So this function, some of its values you can guess, like at x equals 0, the function value is going to be -1. And the reason is that this can't ever be 0, so the only way to get this side to be 0 is if w is -1, this term is 0. So some of its values are easy to compute, but some of its values aren't. So for example, if I asked you what w of 3/2 is, it's very hard. There's no algebraic way you can manipulate this equation that will let you figure that out. So in that situation, you might still care about what the function value is. So what can you do? Well, you can try and find a numerical approximation. So in this problem, I'd like you to try and estimate the value w of 3/2 by using a linear approximation to the function, to the curve. Yeah, a linear approximation of the function w of x in order to compute this function. So as a hint, I've given you, so you're trying to compute w of 3/2. As a hint, I'm pointing out to you that w of 1 is 0, right? If you put in x equals 0 and w of 0 equals, if you put in x equals 1 and w of 1 equals 0 on the left-hand side, you do indeed get 1 as you should. So, okay, so good. So that'll give you a hint about where you can base your linear approximation. So why don't you pause the video?
Everybody 5 minutes.
All right. Come back and we can work it out together.
Here we go. That is the formula you need. And here's the question. Why do we need implicit differentiations? Because we really cannot express the functions in terms of iterated lines and need expressions of the variables. And to the extent that we need to use it, we don't need that neat and tidy expressions. So how do we proceed with this? number 6, calculate a table. 跟住 with number 6, public online discussion forum. Under this spread, okay? You can copy this table, and then you can click on reply, okay? Yes, let's see. Make sure you send me the email. All right? Yes. Okay, check your answer. I hope you got it.
All right, welcome back. So hopefully you had a chance to work on this question a little bit. So in order to do this linear approximation that we want, what we need to know, or we need to know a base point, and we need to know the derivative of the function at that base point. And those are the two pieces of data you need in order to construct a linear approximation. So we have a good candidate for a base point here, which is the point 1, 0. So this curve, whatever it looks like, it passes through the point 1, 0. And that's the point we're going to use for our approximation. So we're going to use the linear approximation. W of x is approximately equal to W prime of 1 times x minus 1 plus W of 1 when x is approximately equal to 1. So this is the linear approximation we're going to use, and we have that W of 1 here is 0. So this is equal to W prime of 1 times x minus 1. Just the W of 1 is 0, just goes away. So in order to estimate W of x, and in particular W of 3 halves, what we need to know is we need to know the derivative of W. Okay? And to get the derivative of W, we need to use, well, we have only one piece of information about W, which is we have that it's defined by this implicit equation. So in order to get the derivative of W, we have to use implicit differentiation. Okay? So let's do that. So if we implicitly differentiate this equation, so let's start with the right-hand side is going to be really easy. Right? We're going to differentiate with respect to x. The right-hand side is going to be 1. On the left-hand side is going to be a little more complicated. We have a product, and then this piece we're going to have a chain rule situation. Right? We have e to the W of x. So we're going to take an implicit derivative, and on the left, so from the product rule first, we take the derivative of the first part. So that's just W prime of x times the second part. That's e to the W of x plus the first part, that's W of x plus 1 times the derivative of the second part. So the second part is e to the W of x. So that gives me an e to the W of x times W prime of x. That's the chain rule. So that's what happens when I differentiate the left-hand side, and on the right-hand side, I take the derivative of x and I get 1. Okay, good. So now I've got this equation, and I need to solve this equation for W prime. Because if you look up here, that's what I want. I want a particular value of W prime. And as always happens in implicit differentiation, from the point of view of this W prime, it's only involved in the equation in a very simple way. So there's it multiplied by functions of x and W of x, but not it's just multiplied by something that doesn't involve W prime at all. And then here it's multiplied by something that doesn't involve W prime at all. So you can just collect your W prime and divide it. It's just like solving a linear equation. So here, if we collect our W primes, this is W prime of x times, looks like W of x plus 2 times e to the W of x. Did I get that right? Looks good? Okay, so that's still equal to 1, and so that means that W prime of x is just, it's equal to 1 over w of x plus 2 times e to the w of x. Okay, so this is true for every x, but I don't need this equation for every x. I just need the particular value of w prime at 1. So I'm going to take this equation then, and I'm just going to put in x equals 1. So I put in x equals 1. Let me do it over here. So I get w prime of 1. And I just, everywhere I had an x, I put in a 1. So actually, in this equation, the only place x appears is in the argument of w. So this is w of 1 plus 2 times e to the w of 1. Okay, so in order to get w prime of 1, I need to know what w of 1 is. But I had that. I had it right back here. That was my confusion. Right, this is why we're using this point as a base point, which is we know the value of w for this value of x. So we take that value. So w of 1 is 0. So this is just 1 over, 0 plus 2 is 2, and e to the 0 is 1. So it's just 1 over 2. So 1 over 2. Okay, so I take that back upstairs to this equation that I had here, and I have the w of x is approximately equal to w prime of 1 times x minus 1. So w of x is approximately equal to w prime of 1, we saw is 1/2 times x minus 1. And that approximation was good near our base point, so that's good when x is near 1. All right, and then, so this is the linear approximation, and I asked for the linear approximation its value for a particular point, x equals 3/2. So w of 3/2 is approximately 1/2 times, 3/2 minus 1 is also a half. So this is a quarter. Okay, so this is our estimate for w of 3/2. W of 3/2 is approximately 1. If you wanted a better estimate, you could try iterating this process. Now you might have or choosing some base point even closer.
Bingo, that you need the knowledge of implicit differentiation to solve this problem. You also need the knowledge of linear approximations to cut intervals. This is a very nice and neat example. You can see more examples of this under this specific page. After class, activity week number 8. All right? So I'll see you back here on Friday for some more examples and also learning how to apply quadratic approximations. All right? Remember, your midterm exam, it's on the last day of this month, all right? So get ready to learn more and discuss with your team members.